going to start the lecture on nanotechnology in chemical engineering. So today we'll discuss about synthesis of nanomaterials. So the nanomaterial aerogels, so that we'll discuss. So in aerogels, what is called aerogels and what are the different methods of synthesis of aerogels, so that we'll discuss. In aerogel, basically silica aerogels, RF aerogel and carbon aerogel, so that will be discussed, and with that we'll discuss about mesoporous silica also. So aerogels we can classify in three different way: inorganic aerogels, organic aerogels, or carbon based materials or carbon aerogels, so that we can divide depending upon the materials it has been prepared. Okay, so if we prepare it considering inorganic precursor, so we can say it is a inorganic aerosols, and if it is prepared from organic precursors for that preparations of aerosol type of material, so then we can it is organic aerosols. And carbon, that is basic or building block material, so that is made of carbons, and aerosols type of structure formations is there, so then we can say it is carbons. When let's say about the aerogels, what is called aerogels, a class of highly porous materials. So various type of porous materials we have studied, so depending upon their pore structure, so we can classify micropore, mesopores and macropores, the porous materials. If it is less than 2 nanometers, then we can say it is microporous materials, or if it is 2 to 50 nanometer within that range, so we can say it is mesoporous materials. Similarly, if that pore structure says more than 50 nanometers, so then we can say it is macroporous material. So now the aerogels, it is, I said, it is a porous materials. It possesses highly porosity is present, and as a result the materials density of that materials would be extremely low density, and its structures also would forms monolithic type of materials. So and it forms a nanoporous solid. So we can say this is our solid materials, and in that so many pores, that pores may be micropores, mesopores would be present. As a result, so solid frameworks that would be present, but very small quantity. As a result, it would be density would be extremely low density, and the structures or the pores, it may be 10 to 100 nanometers, or also in some aerogels the pore structures less than 2 nanometers also is present. And the materials can be prepared by using many methods are there conventionally, or mostly it is prepared by Sol-Gels methods, and then it would be, once it is formations of the gels, the material should be dried. The drying is very important to prepare this type of aerogel materials, since if we heated up the materials at high temperatures, the structures may be collapsed. So as a result, the porosity or other things will be damaged for whenever the materials will be prepared. So therefore, when we prepare aerogel type of material, so drying is a very crucial parameter. So dried special features and then structures will return as a result. So this aerogel type of materials that was first synthesized American scientist Samuel Kister in the years 1930s, and then 1970 it was used as a materials for the storing of the rocket fuels by French scientists using University of Lyon. And these materials was prepared by using the precursor that was used, tetramethyl orthosilicate, that was used as a precursor materials, that is the source of silicon, and it was prepared in an autoclave chamber, high pressure and high temperature reactor vessel that was used to prepare these aerogel materials from silica precursors. And when initially the precursor was taken in a solutions, and then it forms the solutions, and then gradual evaporations of that solvents, it can convert it into gel, and then gels, since here that gels we can dry it at different temperatures and different procedures to prepare the aerogels. So when gel formations is there, then 3D structures or networking structures would be formed in that gels, that particles or materials we have taken, that is tetraethyl orthosilicate. So it would be frame up like the structures formations is there. So when these gel formations or solutions formations is there, we have to take the precursors. So then we can control the concentrations of the reactants, temperatures, pH, other parameters we can control, and depending upon that the structures or different type of gel formation, aerogel formations would possibilities there, then the structures would be different. And conventional evaporations methods, if you want to evaporate, suppose the gel formations is there, inside of gel some solvents is there. So if use conventional simple evaporations methods to remove that solvent from that particular gel, so then there is a possibility chance of means collapse of this structure or frameworks whatever it is formed. So therefore we have to means use some autoclave reactors when this type of autoclaves is there, so where we can use some solvents and precursors, and then we can maintain some temperature and pressures also. By that way we can prepare the gels. So I said the once the gel formations is there by using this type of high pressure reactors. So after that we have to remove that solvent from that 3D networks of that gel formations. So there is various method, conventional normal evaporation methods we can use. Here supercritical drying methods is there. In these methods the gels we can dry by when the solvents, I means the gels we have to heat up a particular temperatures, when the temperature will reach to the critical, above critical temperature of that solvent present inside of that pore. So then at that temperatures the liquid will be converted into the vapors. As a result there would be no surface tensions in between the structures, network structures, and with that solvents. So since at critical temperature is important, so when the materials or gels will be converted into the reach to the critical temperature, then surface tension should be zero at that, at this points liquid that would be in the vapor states, and that vapors easily we can remove from that gels without rupturing the 3D network type of patterns or structures would forms, that would remain as it is. So as a result we can maintain whatever the pore present inside of that gels. Okay, this is supercritical drying method, so that method is very good. And apart from that, at normal temperature of the subcritical dryings also, this way also you can remove that liquid that is present in the gel networks, that is dry gels, in the ambient conditions also we can prepare or we can remove that gel. So here two different way. First one, this is supercritical dryings to prepare aerogels, and this is subcritical drying method. So in supercriticals, here you can see the 3D networks, the gel formations is there inside of the gels, some liquids is there, that liquids we can remove by supercriticals dryings I said. So one supercritical dryings we are maintain that critical temperature of that liquid that is present inside of these pores. So then after that these solvents will be evaporated out, and this type of aerogel structures would be formed. So it having this type of materials possessing extremely low density or ultra high low density. And then subcritical drying also said similarly, once it is gel formations is there in ambient conditions, we can this type of pores are present, liquids are present, that we can remove, and aerogels formations is there. So in aerogels formations, type of aerogels, so aerogels we can prepare silica, alumina, different type of metal oxides that we can use to prepare that particular aerogels. See here I said inorganic type of aerogels, so where these types of metal oxides that can be prepared by using this sol and gel method. So initially that specific precursors, means starting materials whatever, based on that you have to choose that particular precursors, and that we can use, and that is inorganic aerogels would forms. And then after even mixed metal oxides also we can prepare two different individuals metal oxides or two different metal oxides. This type of mixed metal oxides aerogel also can be prepared similarly as particular precursors of these two metals, silica or titanium will be taken, or alumina silica will be taken, and then gel formations, and then drying we can prepare that aerogels or organic aerogels, that is also we can prepare. And for that using we have to use organic precursors, and that organic precursors maybe we can use. So here's resorcinol formaldehyde or melamines perfurols. So these are the organic precursors we can use to prepare organic aerogels. So or this you can see it is RF or MF aerogels. So it was first actually synthesized 1989, and after that it can be synthesized some other different type of precursors by changing these resorptionals or formaldehyde whatever, so that condensation reactions would be taking place. So after that, carbon aerogels also we can prepare by polymerizing organic aerogels whatever we have prepared from the organic aerogels. After that, if we heat up at high calcination temperature, then we can get this type of carbon aerogels. The details I will discuss later. So this type of materials having high electrical conductivity and they are useful for energy storage applications. Also doped aerogels also we can prepare. So doped means whenever let us say inorganic precursors or inorganic aerogels we have prepared with that at different quantity 1%, 2%, 3%, any other metals also we can dope with that particular metal oxides to prepare the doped aerogels that we can prepares, means by using this type of doping. So the particular aerogels whatever we have prepared, its property we can change or we can increase the properties of specific particular property, we can increase or decrease, so depending upon that particular materials that was doped for to prepare that particular aerogels. Okay, and then preparations of silica aerogels. So I said the first one is the aerogel, so that we have prepared. So silica aerogel, so it is can be prepared by I said Sol-gel method. So here's the precursors we have to use to synthesis these silica aerogels is tetraethyl orthosilicate, that would be the Si precursors, silica precursors that we have to use, and or tetramethyl orthosilicate also, either one we can use, TEOS or TMOS we can use, and some ethanol, methanol, that can be solvents we can use, acids we can use, or base also we can use for hydrolysis reactions and polycondensation reactions. So then I said we have to do the drying process, we have to follow once the gel formation is there through this hydrolysis and polycondensation methods, and then that drying supercritical methods, drying methods we can use, or ethanol, methanols, they are used commonly used solvents, and the temperature, critical temperature and pressure, that is usually we use 249 degrees centigrade, that is very low temperature, and pressure extremely high, that can be used for this particular silica aerogel preparations method. So these are the precursors commonly or chemicals we have to use, and in the drying process temperature, pressures we can use this way. So once that materials will be prepared, it's having extremely very low density, means that materials at the ends after drying process we are getting, that's having very low density. And also the materials, this type of silicon oxygen silica network structures formations is there. So in the step by steps, three different steps I said, initially gel formations, then aging, and then drying process. So the reactions will take place with the precursors. First one is the hydrolysis reactions. This was our precursors, ethyl or tetramethyl orthosilicates that we have taken, and with waters this type of hydrolysis reactions will take place, and then this react with initial precursors we have taken, and then this type of structure silica oxygen silica bond formations is there, or maybe this react individuals, and this type of structures condensation reactions may take place. So silica oxygen silica, this type of frameworks may forms, okay, by hydrolysis and polycondensations methods. So monomer to dimers, and then polycondensation, then silica gel formations would be theirs. Okay, so in these gels this type of framework or structure is formed. Here's the pores will be developed, and there's it is filled with the solvents, that liquids that we have taken, and after that we have to remove this by drying methods. So here step by step methods you can say. Initially I said precursors you have to take, then solutions formations is there, and then by slowly gradual evaporations of the solvents we can get gels, and then agings, the other liquors, and then washings, solvent exchange, and then supercritical dryings, that is the very crucial steps. So I said that any solvents whatever that is present in this network, so that solvents we have to use by supercritical drying. So by changing temperature, once it is reached at this critical temperatures, so above that, so liquids does not present in that force in the forms of liquid, that would convert it into the vapors and easily can be removed. As a result, these networking structures remain as it is when it was prepared. Okay, so silica gels, how silica aerogels, how that can be prepared by Sol-gels methods, and the drying methods is different. So as a result, the structures would be little bit difference means various pores means micropores also would be present in this type of silica aerogel. So, how silica aerogel is different from the mesoporous silica. So, mesoporous silica also we can prepare. We these sol gels methods we can use to prepare mesoporous silica. Silica aerogels also we can prepare by sol gel method, but here dryings we have to use supercritical dryings. Here you can see that basic difference in between these silica aerogels and mesoporous silica. Both are made of silica precursors that treat ethyl orthosilicate. But here's the pore structures you can see in the silica aerogels. Mesopores is present. Here's also silica, mesopora silica. There also mesopore is present 2 to 50 nanometers within that range. But in additions to that, since this is when we are preparing silica aerogels, we are not using conventional drying process. So then micropores also that is present with the mesopores. So the pore structures having smaller diameter less than 2 nanometers that remains as it is. So therefore this materials is better in terms of more other pores also remains theirs, but in this case mostly that is destroys micropores is destroys in this mesoporous silica. And see here the pore structures is opens and it is orders in case of the mesoporous silica hexagonal types of pores that arrangements is present, and it is opens type of structures of in case of the silica aerogels. So now RF aerogels, so that also we can prepare by condensation method. So in this case, once we are prepared a resorcinol formaldehyde aerosol type of, in this case resorcinols that precursors of chemicals we have to take, and formaldehydes also another chemical reagents that we have to use in aqueous mediums. And so there we have to use sodium carbonate as a catalyst, sodium carbonate that you have to use as a catalyst for 3 hours room temperature if we mixing up and the reactions goes on, and then gradually the gel formations would be there, and the gelations temperatures we have to use 85 approximate degree centigrade for 6 hours long period of time. So you have to use for mixings for formations of the gels, and then you have to dry the gels whatever the gel formations is there by reactions with resorcinols and formaldehyde condensation reactions to take place, and then the gels you have to heat it up by low temperature. So then we can get RF aerogels. So here's you can see this is RF aerogel. So here's this is the precursor resorcinols and formaldehydes that you have taken, and I said sodium carbonate that was as a catalyst, and then this type of networks or RF resorcinol formaldehyde condensations whatever would form, so that structures would forms. And here it is the ACM image of RF aerogels. So same image you can see, so whatever it is formed, so the pores are also present. So here, so this we can prepare this way. Okay, so then whatever the RF aerogels we have prepared, so that is by condensation reactions in presence of sodium carbonate as a catalyst. So these RF aerogels we have prepared. Once this RF aerogels is prepared, then we can heat up in absence of airs at a high temperature, extremely high temperatures 11 approximate 1100 degrees centigrade if we heat up. So then in presence of inert atmosphere, so then these carbon aerogels would forms. Okay, so this carbon aerogel consists of high surface area. Therefore this type of materials can be used for electrical conductivity where it is suitable, highly conductive, or you can use supercapacitor fuel cell application, there it can be used. Okay, so now the properties of the aerogel, so whatever we have prepared, so I said micropores is also present. So it materials is highly porous, as a result pore diameters micropores is present, mesopore is also present, and extremely high surface area also that materials possessing. So 500 to 1500 meters per gram, the extremely high surface area that materials having. Also thermal conductivity would be very low, so sometimes that materials can be used as an insulators for a specific applications. So since the materials means the aerogels materials whatever we have prepared, so that having extremely lightweight, therefore these materials least dense materials we can synthesize or we can use for specific applications. So whereas the materials having lightweight, so each a particular specific application there we can use these materials. Sometimes you can use as a insulating materials also. Since the materials having low refractive index, so therefore the materials also can be used as a transparent property. And slow sound propagations means the materials having speed of the sounds through this aerogel is extremely low, therefore slow sound propagation. So where it is soundproof materials is required, so there these materials we can use as a soundproofing materials or systems developments, there we can use. Also the materials having a low mechanical strength, also this type of aerogels materials, so we can prepare the aerogels that having low mechanical strength, therefore the material sometimes is fragile in natures also. And super thermal insulators, I said the materials having extremely high force and sometimes the thermal conductivity is very low, therefore these materials can be used as a and insulating materials for specific applications. Okay, so some other applications or the details of different applications of these aerogels means since my catalytic property, also these materials as a catalyst support materials also we can use. Sensor material, fuel cell applications, filters for gaseous pollutants, so many places we can use these materials. Also thermal conductivity is it very low, electrical property, acoustic property, optical properties, they are mechanicals also. Different places we can use these materials, catalyst materials or gas filter materials and soundproof roof developments, there we can use dielectric for ICs and capacitors, optics, energy absorbers, many places we can use these aerogels materials. Okay. So now for a silica I also said, so that is also similar type of materials. These materials also can be prepared by surfactant template route also, but this material is little bit different from the aerogels that already have discussed. So these materials we can prepare by surfactant template route. So here surfactant materials we can take, then that surfactants we can put in a solutions, there acids or other chemicals we can use, micelle formations is there, and after that silica precursors, whatever ethyl orthosilicate, the precursors we have taken for silica frameworks, so that would be distributed at once the micelle formations is there. So after that condensations reactions through the agings or hydrothermal process, and then this type of organic inorganic silica template composite formations is there. So after that we can remove that template by calcinations or heatings up by oxidation. So then this type of inert insides, whatever the surfactants micelle formations is there, that would be removed, and then various pore developments would be there. So that is called mesoporous silica, SiO2, but mesoporous silica. So pore structures is 2 to 50 nanometers within that range. So the diameters of the pores, so nanoporous materials or pore structures is within that nanometer, so that can be prepared. So this silica depending upon different surfactant templates, so we can prepare this porous silica, and depending upon theirs we have structures, method of synthesis, different type of morphology may forms that porous silica. So mesoporous silica, hollow sphere silica, core cells spheres or oak cell spheres, so different type of silica nanoparticles we can prepare depending upon method of synthesis and the precursors we are using, so depending upon that. So, okay, similarly also this already I have discussed. So here's polystyrene was used as a templating agent for, and CTAPs was used as a surfactants. So in this particular process also similarly CTAP surfactants that would forms this type of micelle, and after that silica precursors polystyrenes that would be as a templates. So in polystyrenes this type of structures would forms with tetraethyl orthosilicates and CTAPs, whatever we have taken surfactants. So yeah, this type of polystyrenes and silica composites micelle would forms, and then after that we can remove the CTAPs and polystyrenes, and then this type of porous silica particles will form. So that having pore diameter 2 to 20 to 80 nanometers, this silica so we can forms. Hollow sphere silicon also similarly we can prepare hollow sphere silica. So here these spheres or silica particles or nanoparticles whatever we form, it is dual templating methods in this particular materials. So here you can see outer shell is porous and inner shell also, that is whatever that is voids that is formed. So that initially it was solids, inner shell it was initially solids, carbonious sphere, so that was prepared from organic polymers or metal oxides or other kind of materials we can use. And after that, this inner core that was removed by calcinations or other methods, so we can remove that, and this type of porous hollow silica nanospheres may forms. Okay, so here's the precursors that was used. D glucose as a template materials was used, and sodium silicates that was used as a silica precursors. So once this type of glucose remains inside of the cores, we can heat it up in presence of airs or oxygens at high temperatures. We can then that would be removed once it is heated up at high temperature. Then porous silica, hollow sphere silica, highly porous materials that would forms. Okay. Similarly, this method is also similar. So here's hollow spheres that we have prepared. So here also similarly TEOs as a precursors we can use, and these are the metals oxides, means polystyrene spheres or RF resins also we can take as a template material. So template materials we have taken, see here template in the suitable solvents we have taken, and after that TUS surfactants we have used, and that would be distributed. Some whatever the templates you have taken, that was remains inside of the cores and outer sides or cells, tetraethyl orthosilicates whatever that remains outsides. So after that, if we heated up calcines at high temperatures, the cores will be removed. So cores, these organic materials that is present, resorcinal formaldehydes, polystyrenes whatever, and some metal oxides is also there. So that metal oxides we can remove by using etchings method. So we can remove by that way these mesoporous silica hollow spheres that would forms these methods. Almost all the methods whatever we have discussed for mesoporous hollow spheres silica, mesoporous silica preparations, so almost all methods having silica precursors that we are using, and another materials that is we are using as a surfactants, that may be metal oxides, any organic surfactants we can organic reagents we can use and to develop insides core, and after that by calcinations or some etching methods we can remove that, and different type of depending upon that concentrations and the templates we are using, the structures would develop. Okay, and so already we have discussed. So this mesoporous silica or aerogel type of silica aerogels whatever we have prepared, so that can be used many applications already we discussed. Catalysis means for the support materials or itself as a catalyst for various reactions we can use. So here's gold mesoporous silica that was used for 4 nitrophenols to 4 aminophenols, that reductions of the nitro groups. The gold mesoporous silica that was used, that is core cells silica, that is nanoparticles that was used. So like that many applications are there. So here's this aerogels silica or carbon aerogels or silica mesoporous silica materials that can be used as a support materials or as a catalyst materials from chemical point of view. So many applications are there. These materials can be used many way. Today is up to this. Thank you.